Okay, so we are going to have Nathan for our next presentation. And Nathan is currently a PhD student with Professor Dr. Mark Moons, and he's working on causal representation.
Should be working, right?
Yeah. Right, I use these to go back and forth. Cool. Okay, hi everyone. Yeah, so I'll be talking about causality and representation learning, and specifically as a tool for dealing better with distribution shifts. That's like the end goal I'm really interested in. I'll give a bit of a general intro of some of the concepts that are useful for the things I will talk about, and then there's really like two sort of parts, two approaches, let's say two attempts that I took at this. So first, I'll be, the framework I'll kind of be using is that of structural causal models. I think the framework that you're probably familiar with talking about causality is Bayesian networks, which in a graphical way sort of show, well, which variable causes which, and you can deduce all kinds of conditional dependencies from that. And structural causal models are really much the same. The point is kind of that the stochasticity is sort of pushed to the outside, so you assume there are these deterministic mechanisms, like with the same input, they will always give exactly the same output, and the reason that it's a little bit stochastic is because there are these external noise variables, which are also assumed to be independent. And the reason we take this view is just because we want to make some assumptions and talk a bit about those mechanisms. So the connection to out-of-distribution performance kind of starts with this assumption called the independent causal mechanism assumption, which is that within a distribution you have your variables, which have a certain distribution, but among different distributions, you might have different causal mechanisms, like the F's themselves might be different. And the assumption is that they are not correlated over different distributions. So if one mechanism is different, it doesn't really imply that the other one will be different. And following from that is the sparse mechanism shift assumption, which basically just states for distributions shifts we are interested in, hopefully they are sparse from this lens of the mechanisms, so only one or a small number of the mechanisms shifts. Yeah, and then also to be noted is if we don't immediately have access directly to what our causal variables are, but we still need to disentangle them, that the assumption is that the sparse mechanism shift assumption only holds when having the perspective of the correct disentanglement. Like when you look at sort of a mix of the variables and see like what would their mechanisms be, then it's no longer sparse, like all of the mechanisms here need to change. So we're looking at exploiting this sparse mechanism shift assumption in two ways. The first one is we'll try to only use parent variables to predict a variable. So for example, predicting Z, you could predict it quite well using Y because it's correlated, might have a lot of information about it, but the parent is X. And the idea is that if you in domain learn to depend only on the parent, if some other mechanism changes, you might get away with not needing to update your model, while if you depend on spurious correlates, like non-parent correlates, there's a higher chance that you'll need to update your model. The second one is basically what I was saying before, that you want to try to have a disentangled representation of your variables so that when you want to predict all the things here, when you want to predict both Y and Z, you might get away with only needing to update a small part of your model, rather than if you have an entangled view, you'll need to update everything, and hopefully only needing to update a small part is faster, easier, something like that. Yeah, so then for the first kind of view, there was this paper we did. The motivating example is visual linguistic tasks like visual question answering. So you have here a question: why is the man upset? Either he stepped into a puddle or he stepped into some dog droppings. And in your source domain, you might have always seen that umbrellas occur whenever there is rain. And so both a causal model and a non-causal model might work quite well in a source domain. A causal model which uses rain to predict the presence of puddles, and a non-causal model which uses umbrellas to predict the presence of puddles. In the target domain, however, maybe umbrellas occur without rain, and the mechanism for umbrellas change for some reason. For example, I have here the Hong Kong protest. In that case, the non-causal model will look at the umbrella, will say, there is a puddle on the ground, so the man must be upset because he stepped into a puddle, but it's not true. For this paper, I was basically looking into an existing technique and kind of checking whether it actually works. And the technique has to do with automatically deconfounding. So I'll first say what deconfounding means. The idea is to detect whether some correlation is causal or not. For example, we might have this causal model there. We see a certain correlation between umbrella and puddle, and we wonder if it's actually causal. Ideally, what we would do is change our data, do some intervention, like take away all of the umbrellas and manually change the mechanism there, and then see whether then still there is a correlation between umbrella and puddle. But typically, or often for observational data, you can't really do that. So you can approximate it, like mathematically, under the assumption that you know all of the possible confounders, and you know the state of rain here. You can simulate the effect of an intervention by basically controlling for the confounders, and mathematically, like I won't go too much in details, but at some point you just use the prior probability of the confounders instead of a conditional probability. And auto-deconfounding is a technique used by a few existing papers which tries to pre-train a vision language model as if the training data was deconfounded in the first place, in the hope that you then learn to only ever depend on the parent. And I don't really have time to go too much into the details, but roughly what they do is they represent the different variables, x, y, and z, and so on, as just vector embeddings like you do all the time with neural networks. They then store a big dictionary with average embedding for each object, which is called the confounder dictionary. And from that, they use a certain attention mechanism to each time retrieve relevant confounders and use those to deconfound. And this prior weighting step I was talking about before, which does weighting by the prior probability instead of the conditional probability, they approximate that, let's say, by taking a prior weighted average of the embeddings. This is very high level, but you can ask me more offline, I guess. So there's a few reasons why there might be an issue with this. So one is it wasn't really measured whether confounders, the correct confounders were found, and that is important. You cannot just control for any variable. If you control for like a downstream effect, you might actually mess it up. And there's this thing called the causal hierarchy theorem, which says that without certain extra assumptions, you cannot really expect to find your full causal structure. The second one is that there seem to be some assumptions missing about whether the implementation is actually equivalent to the theoretical meaning of deconfounding, whether this auto-deconfounding thing that uses this confounder dictionary with embeddings and approximates the prior in some way. And then finally, we did some more ablations on what is the link of deconfounding with the actual OOD performance improvement that was reported. So for the first question, we gathered some ground truth data with human annotated data with Amazon Mechanical Turk. labeling causality between different objects. And what we saw was that the confounder finding ability was actually not consistently better than random. So there's a bit of a doubt there. And also that the OD performance there wasn't really correlated with how well you found confounders. The second one is that we showed that there are some additional assumptions needed for the implementation to match theoretical deconfounding, such as the fact that all the confounders need to be mutually independent and that you need to have enough, let's say, representational capacity in the vectors that you retrieve from the confounder dictionary. And then finally, what was also a bit disappointing is that in the ablations we did, like keeping the code book but removing the prior weighting, or even comparing to the baseline, which doesn't use any of this on a more like-for-like basis, we saw that most of the improvement disappears. Yeah, the first attempt here, this auto-deconfounding, which seemed quite promising, wasn't really the way in which causality can help our distribution in our view, and it has a few problems with finding the correct confounders. If you would find the correct confounders, are you really deconfounding correctly? And if you're really deconfounding correctly, is that really helpful for the OD performance? It's kind of a negative answer on those. And so we're interested in investigating, and we're still believers in that causality can help, in investigating a setting when we know we have access to the true causal structure. Yeah, we need to be explicit about the assumptions, and we compare on a like-for-like basis. So that's what we try to do with this second paper. It's called Causal Factor Disentanglement for Few-Shot Domain Adaptation in Video Prediction. So I kind of break down the title here. Video prediction, the reason we use it is because conveniently there is time in there, and we know that causality goes from the past to the future, so it helps us a little bit. And also it's useful. You can imagine some applications that for really predicting the next frame, like not just some label about it, could benefit from that. Few-shot domain adaptation is interesting because, as you also know, models work best when you have a lot of data, but getting a lot of data can be quite expensive. So if we can do quite well with only a few samples, that's interesting. A way to do that is if you have a lot of data from a related domain, think how you can best leverage that, so how to best do transfer learning. And so the reason why we might think that this causal factor disentanglement might help is basically 3 works in literature which kind of suggest they could be put together for this. The first one is one that motivates the sparse mechanism shift assumption as reasonable. And so basically what we do is we then assume that holds. The second one is something that relates speed of adaptation with correctly identifying the underlying causal model, so correctly disentangling the variables of interest. And in this work, speed of adaptation is the tool and the end goal is identification. And so we try to kind of reverse it. We try to use another way of identifying the correct variables as a tool to then improve speed of adaptation. And this final method is something that does that for us, that can identify the causal model. It needs some additional assumptions, so that's a bit of a limitation, I guess. Yeah, but so we try to then repurpose it for our goals of domain adaptation. Okay, so yeah, just to reiterate what we mean with causal factor disentanglement, the point is that in a lot of typical Bayesian networks, you might see like correlation between cigarettes smoked and number of lung cells inflamed. Your variables are given to you already in some tabular form, and you can just start working with that and think about causality between that. But if you have a video frame evolving over time, the variables given to you a priori are pixels, and it's not so clear that these are the variables between which you want to search for causal. It's not like the left top pixel, it's very useful to say that's the cause of the right bottom pixel in the next step. So you want to first extract higher level variables between which to search for causes in the first place. Yeah, such as color or orientation. And so our idea here is we have certain video frames, and we assume that indeed underlying them are some high-level factors like position, color, and so on. And the frames evolve over time, and that evolution can really be explained by a evolution in this high-level space with certain fixed mechanisms for the different factors. Yeah, and then each time a sort of view from that. So that's an assumption we make on the true process. Then what we try to do is first go back to that high-level space. So we try to disentangle so that in our latent vector representation, all the information about position is in this part of the vector, all the information about color is in this part of the vector, and so on. And then we try to predict the future in that latent space. Yeah, with some shared parameters and then some specific parameters, which tries to predict this next step. And then with like an inverse encoder, we go back to the next frame. The idea here is that not only is these latent activations sort of disentangled, but we're trying to disentangle the parameters. We're trying to make the subset of parameters which are really only responsible for predicting a part of the vector, and so ideally they are only responsible for modeling a certain mechanism, so that when the sparse mechanism shift occurs, one or a small number of the mechanisms changes, we might hope to get away with only a small number of the parameters also adapting, hopefully adapting more quickly. Yeah, so to the way that we set this up is we compare models with the disentanglement encouragement that we get from the citrus method to a default model, and there are a few different backbones we try, and we try it on different data sets also later. And our main interest is in comparing like the green and the red model here and seeing which one is better OOD. For the data, so we have a few requirements for our data. So it needs to actually be mechanisms induced. You can also imagine just random pixels evolving over time. That wouldn't really work for us, like the assumption wouldn't be true. It also needs to be able to be disentangled by this particular method that we're using. And there's some extra information that it needs for that, which I won't go into detail about now. Finally, also, the sparse mechanism shift assumption needs to hold. And for the first two, there is some existing benchmark which satisfies them with two like variants of the dataset here, and it's synthetic. So that's also a bit of a limitation I'll discuss later. For the final one, that wasn't yet satisfied, so we make some variations of that benchmark so that we have a bunch of variants in which there is a sparse mechanism shift. The two metrics we're interested in is, well, how well did it actually succeed in disentangling, which is kind of a combination metric, and then our end goal, what's the OD prediction error just in pixel space. Yeah, and the results, I'm also not really showing graphs here or going into much detail about that, but you can ask me later. Very broadly are that they're kind of mixed. So we see that in our different data sets that we test and with different backbones, the disentanglement only really succeeds for one of them. And we do see within that subset that it helps the few-shot OD error. And looking more broadly across the different settings, we see that we see a sort of positive correlation between disentanglement and OD error. But there are some notable exceptions, like where the disentanglement is really quite a bit worse and the OD error is still smaller. So indicating that the picture is not quite as perfect as like the original hypothesis. And the problem or the explanation, we think, is that the whole point here was to try to localize the parameters that need to be adapted into quite a small subset of the parameters. But what you might have, if you don't explicitly pay attention to it, is that other parameters, like the encoder, whose original only job was just to recover these latent variables, it didn't really need to think about predicting the future. if you do nothing, it will already think about predicting the future, and it will specialize to the old mechanisms. And if those specialize to the old mechanisms, when the new mechanisms come, they will also need to adapt, and it kind of breaks the localization there. Then finally, more broadly, this and other literature works on synthetic data, often things that work with disentanglement or identifiability do, where we know the ground truth causal factors and causal mechanisms. And it's understandable, like given in the first paper, it was working on real data, but it was not so clear what even the true causal connections were there, and they weren't really like correctly found or found in accordance with what humans thought. But it's a bit of an open question how to how to define what the correct causal variables are in real data. On the most accurate level, you will just want to model, you know, for a video, all of the atoms and just the evolution of the laws of physics, but that's completely intractable. So on a higher level, we use these abstractions like cars or the wheel of a car, a door, colors, positions, and so on. But there is some like inherent freedom in what you choose there. So yeah, for me, it's still a bit open. If there's no fundamental ground truth there, like how do you decide what to pick? Probably the answer is somewhere in lines of whatever turns out to be useful is what we should use. And maybe in our case, it's for whatever, you know, slicing of the data, the sparse mechanism shift, for example, holds. That is what we call the truth. Yeah. So that's it. Thanks for your attention.
Thanks very much for the talk. Do we have some questions for Nathan?
Yeah, thanks for the interesting talk. So you mentioned these Bayesian networks and this probability calculus basically, which is like, I think, a really powerful method for causal inference. Mm-hmm. But we humans also use like all kinds of heuristics when we reason about causality and do inference. So is there like a way to integrate any heuristics in the approach that you're using?
Yeah, that's a good question. I can imagine, for example, from text, from like language models or so, you can probably, if you ask a language model like what causes what, just because it will have seen in text a lot, like, oh yeah, this is the cause of that, even if it never actually saw the statistics and saw the randomized control trials that prove it, that could be kind of a good source of heuristics, or I guess a sort of common sense in some way that everybody just knows that the rain causes the puddles because we see it fall and stuff like that, and you don't really need to deduce it from a lot of observations of rains and puddles and umbrellas. So yeah, just off the top of my head, I can imagine using the common sense of language models for causal identification could be useful. Yeah. So.
Okay.
Any other questions? Okay, then thanks very much for Nathan's interesting presentation. And then we'll